So first of all, motivational slide. So this is styled and optimized GEMM kernel, and it's styled and optimized GEMM kernel, which fits into a single slide. So it's quite an achievement. So what exactly is Wave? This is Symbolic domain-specific language for high-performance machine learning. It's targeting GPUs, currently AMD GPU only, but it should be able, enable other vendors if needed. It uses Python syntax and symbolic expressions for the kernels. It does explicit separation between high-level kernel logic and distribution strategy. It uses MLIR for code gen, mostly upstream dialects, and it uses IREE as last mile optimizer and as a runtime to actually launch kernels. So why actually do we need a new language? So all modern machine learning workloads require hardware GPU intrinsics, matmul intrinsics to use for the good performance, and all GPU vendors have them in some form, and the direct programming in CUDA or heap is very error prone and time consume, and those intrinsic usually collective operations working across many threads not fits into usual SIMT model, needs some non-trivial data layout in registers or memory, and there are tiling and scheduling which is intertwined with logics. So we need a more convenient way to write high-performance kernels. There are other languages which are working on this, and they are trying this, but we still believe we can provide something novel, and to provide more convenient way to write kernels. So in our case, we have our high-level kernel description operating on whole tensors level, our tiling distribution strategy, separated from the actual kernel description and can be changed without changing kernel. The language tiling and distribution operating on GPU block, aka workgroup level, which is then later subdivided into wave level. We are using symbolic data types for tensor shapes and for the distribution patterns and for some other things. When we have distribution and kernel memory access pattern for blocks and threads decided by the compiler transparently, we are using masking for the unaligned shapes, masking vector ops, and it's generally an easy way to test various hardware, matmul hardware intrinsics, which all require different layouts and such. So let's see first for the simple element-wise copy kernel, just to see basic constructs. And so there are three basic parts, which is kind of out of order here, but so we have a distribution description, which is called constraints. So we specify how divide our block and how divide entire work into blocks and then into waves. We have kernel body, and in this case it's really simple. So it takes two tensors, read one, write to the other. All tensors are symbolic, m by n, and so on. And finally, we had a final part when we specify actual symbol values, and then we compile kernel and run it. So here's GEMM kernel again, and now we'll look at the actual parts, actual important parts. So we have hardware constraint, which describes threads per wave, basically wave size, and it describes it sets MMA intrinsic to use for MMA operations. We can set MMA also per ops, but sometimes it's more convenient to set it globally. We have assumptions. So for dynamic DIMMs, we can specify some properties which can be used by compiler for optimizations. So we have tensor descriptions, which are shape, data type, and also address space, which controls should we promote this to shared memory or not. We can allocate temporary storage using register, and this is virtual register, which is has a full MMA shape, full matmul shape, m by n. And then we have reduction loop across key dimension, and this is normal matmul. So read two arguments, call MMA op, which will be converted to the actual intrinsics, and then write the result. So this is a slightly more complicated example. So this is convolution through the implicit GEMM. And if we go to the parts, so the kernel itself looks almost exactly as a normal GEMM, except we have 4-dimensional tensors as inputs and outputs, and we have special thing called mapping. And mapping describes how to map 4D convolution inputs to actual 2D input expected by MMA. And it's kind of similar to MLIR Linalt generic when you have iterators, which corresponds to generic parallel iterators, and you map output to I and J and map input to using these formulas how to actually translate element position from the input to output and outside. We don't have reduction iterators yet. We have also indirect iterators, which I don't have in slides, but they basically allows indirect reads or writes. And here we have part of the attention kernel. Unfortunately, attention doesn't fit entirely into a single slide. So, and it's more complicated. So it has two MMAs inside the reduction loop. It have also reduces across work groups. It has global max and global sum operations. It has direct iteration index access and some more advanced features. So let's go to the actual architecture and language architecture. So front-end, middle-end, back-end as usual. So for the front-end, we're using torchfx tracing. For the middle-end, we're kind of using torchfx as intermediate IR. We would like to switch to MLIR fully at some point, but we are not there yet. So we are doing some important transformation here, and finally in backend, we are doing upstream. We are using upstream MLIR dialects, vector arrays, STS, SCF, MDGPU dialects. We are using IREE as last mile optimizer, and we are also using IREE as runtime to launch kernels. There are also some ongoing work to enable standalone runtime, which doesn't require IREE, but it's work in progress. Okay, going to the front end. So we are using torchfx. We are using torchfx tracing. So trace basically just calls your kernel body with special proxy object, which constructs the actual calculation flow inside kernel. So with tracing, you don't need the actual Python parser to parse kernel, and you can enable kernels compilation pretty quickly. But as downside, basically you need special handling for the control flow, as you can, if I switch back to the code example, the reduction loop is actually a function wrapped into Python decorator, so it's okay. And we are using, and torchfx itself is basically another intermediate representation. It's Python-based IR, SSA. We have our wave-specific operators and types. We are using symbolic types from SymPy to do symbolic calculations. And we are leveraging some torch infrastructure for graph rewrites. So on the important transformation, so we have index sequence analysis and thread shape analysis. Basically, MMA instructions require non-trivial data layout. So we start from the MMA nodes in the execution graph and then propagate shapes backwards and forwards through the graph, through all nodes. There are some code to resolve conflicts when you have different layouts, conflicting layouts when you arrived from the different directions from the multiple MMAs, for example, some broadcasts or even worst case, moving to shared memory and back. And there is also a thing called expansion. So in our case, we have waves for which we can set basically any tile size, but to map it to hardware intrinsics, they usually have fixed size, something like 16 by 16 by 16. So you may need to basically unroll stuff and generate sequence of call to the intrinsics. So yeah. We have a bunch of we have a bunch of other optimizations happening in torchfx stage. I won't go like into much details into them. It's basically some shared memory layout optimizations, barrier insertions, like partitioning reads writes when they're not actually like contiguous reads or writes, and stuff like loop hosting and stuff like that. So if we go to the backend, so to the actual lowering, we are using affine apply and affine expressions to lower symbolic types, to lower like symbolic calculations from SymPy. So they're basically lowered to the affine apply when it's directly mapped, can be directly mapped to the affine expressions, and otherwise we are just generating like sequence of the like IREE ops can generate selects and such. Like we also can generate. Sometimes we need to generate vectorized index calculations. So affine apply doesn't support this currently. I have draft PR to enable affine apply on vector types. I'm not even sure at that point I want to proceed, but yeah, it's there. So prior to lowering, we are calling SymPy simplifications functions to simplify expressions before. And then when we're done with expressions, so we'll lower the rest of the operators. So read is lowered to the like vector read, vector gather, vector mask load, writes like to store, scatter, and mask store. MMA lowers to currently to MDGPU, MFMA intrinsics, reduce to GPU shuffle, and we have some special we have some also instruction scheduling code. It's not very advanced at this point, but we still can do this, and we are lowering, and we are using like MDGPU specific instruction barriers, intrinsics to like limit instruction movement between areas. And after all of this, everything is lowered to LLVM IR, and then to the compiled for the MDGPU. And also we are using IREE as runtime. So we are using IREE infrastructure to be able to launch kernel. So the output is our language is just like GPU func with some GPU code. And IREE provides all the necessary host infrastructure to run this kernel, to do interop with PyTorch, to use PyTorch tensors with minimal overhead, which wasn't really minimal overhead, and there are some issues here, but we are working on it. And so we can just call our GPU kernel with PyTorch arrays, and we can just call our kernel from Python, and we can cache it, and we do stuff like this. And there are few important optimizations in the backend, like in the actual, not really backend, but backend in the sense in the MLIR part. So we are using like normal vector and IREE dialect canonicalizations. We are using like MLIR CSE, and we are using integer range analysis from IREE. So integer range analysis technically is upstream, but in IREE there are some improvements over it. So what we are doing, like we are reducing number of casts between integer and index types. We are reducing some, like it's often possible to reduce like 64. So all index calculations initially generated as I64, and we are using integer range analysis to reduce this to I32 if possible. If int is like fits into the range, we are doing like it is doing divisibility analysis. So you have 64 like you have, for example, 64 threads, and you can end with like expressions, thread ID modulo 64, and it can be like removed entirely from the code because we know we have like 64 threads, so we can do this. And so some important things we learned from this. So the compiler itself, so the language itself is completely Python. So users write kernels in Python, but the language itself, the compiler itself, is also written in Python. We are using MLIR Python bindings, Toxes MLIR. Like using Python for the compiler has its like pros and cons. Like the compilation speed like definitely suffers when you're using Python. Like it's partially offset, but by the fact we can cache kernels, like we can cache kernels in memory and we can cache kernels on disk. Like, and also not all MLIR things are exposed to Python, which is expected because like MLIR is like C++ first, and basically we are adding like missing things like as needed. On Torchfx side, so Torchfx is like minimal IR. It is good to enable like front-end stuff and to quickly enable like end-to-end flow. We had to re-implement some common utilities on top of Torchfx, like CSE, dead code elimination, and such. We would really like not to do this and use MLIR directly, but it's not fully possible at this moment. And so going to the question why we cannot use MLIR like fully in the compiler, so we heavily rely on symbolic expressions in the language, and there are no like good symbolic expression type and symbolic tensor type in MLIR. Like there is nothing in upstream MLIR. There is like affine expressions which cover some cases, but not much. And honestly, I don't even have a good design how this symbolic types should look like in MLIR, and also at the same time work efficiently. So this is open question, but we would really nice to have one, and like we are open to collaboration. If someone has any ideas, we'll be very happy to like cooperate. And also on IREE side, IREE actually really good to enabling end-to-end flow, like to quickly enabling end-to-end flow. So from our side, we only needed like to write GPU kernels, and then like just few lines of IREE custom like flow dialect and another flow and stream dialect, and few API calls, and it's like allowed to like enable full end-to-end flow. So you can pass PyTorch arrays, you can run your kernel from Python and such. And it would be really nice to have something like this in upstream MLIR. I'm not sure how good it like fit this Python PyTorch stuff, but it can be discussed. But yeah, anyway. And yeah, that's all. So the project itself is open source. It's on GitHub. You can check it. We also have a discussion channel on the IREE Discord, so you can join and ask questions. And also we are hiring currently. So if you are interested to work with this, we'll be really happy to listen from you. So yeah, that's all. So questions.
Thank you, Ivan. Questions, please.
Thank you very much for the talk. I have two questions. One is, how do you compare Wave with Triton LAN? And the second question is, what is the performance of the kernel that you see, which is written by Wave versus a peak performance that's maybe the kernel manually written?
Yeah, so comparing to Triton, so Triton is good, but it have some issues. You have like to write this indexing expressions like pointer mask stuff, and you have right to masking stuff, and you still have like kind of tiling decisions intertwined with actual kernel logic, while in our case we strive to like to have them fully separate. So we have high-level kernel and then have like distribution and tiling specified like completely separately. So you can switch between them without do too much changes into the kernel. And also Triton contains like basically this direct calls to thread ID something. I don't remember, but ID something, and this ID calculations is also completely abstracted in our case. On performance side, so we are currently comparing. So we are currently comparing with AMD GPU Triton, and we are mostly like on par. Sometimes slightly slower, sometimes slightly faster than AMD GPU Triton. This is for the attentions. For the GEMMs, we compared with HIBLAST some time ago, and we were also at least on par with it. So I would say performance is pretty good, considering like how easy to write kernels.
Like Triton is about 10 to 20% of peak performance, right? So are you saying that Wave is on par with Triton? Or?
I mean, our main target at this point just to be basically just be on par or better than Triton.
Okay. Thank you.
Yeah, I have a technical question. You mentioned symbolic types. Do you have dependent types, or is it just symbols and tensors?
I mean, we're using symbols for the like we are using symbols for the like tensor dimensions, and you can do like non-trivial dependencies between tensor dimensions. Sometimes we are using symbolic types, like symbolic types and symbolic expressions effectively in the similar way for the mapping. For example, we are using in the similar way you will use it, for example, in linear generic for the affine maps. So,
yeah, so this is not full-fledged dependent types, and that is something that is easier to model in MLIR, answering some of your PS. If you had real dependent types, that would have been much harder.
I would say I would really want to have like symbolic tensor type in MLIR when like each dimension of the tensor is actually like some symbol on some expression. But I don't have, like at this point, I don't have a good design how actually it should look like in MLIR.
Come to the open design meeting.
Yeah.
Thank you.
Definitely.
More questions? Okay, let's thank Ivan for the good talk.
Thank you.